installation of the dielectronic resonators antenna using CST software. So as you can see from slide, this is CST Studio software. And before I start to design our project, of course we need to first create a new project template. And there is some details we need to be alert is we can see at our right hand side, the units is always in mm and gigahertz, and I'll be setting the frequencies from 2 gigahertz to 6 gigahertz. So now we come to my project. This is the project that I have done for my FYP. So I'm now to explain the process of designing the ERA. So for the first step, we design the ERA is we will building the ground plane. So of course I will be build a brick for my ground plane, and the size will be 30 times 30. And negative 3T here is for the thickness of the ground plane, and it is always be 0.035 mm. So after we had built the ground plane, we come to our slot. Okay, the slot is also at the surface of the ground plane. But before we build the slot, we need to have a little bit calculation using some equation. So this is the first equation for counting the length and the width of the slot. So the first equation, we need to have a value of the respectivity of DRA and subtract of DRA. So we assume have 10 and 2.33 divided by 2, and we get 4.483 here. So after we get 2.483 here, we will now come to our formula for the length slot. The length 0.4 divided times lambda. Why lambda is 74.95 here? Because I use frequency for 4 gigahertz, and when you apply the 4 gigahertz to the wavelength calculator through Google, it came up 74.95 automatically, and we divide by 2.483, and we get the length 12.07 mm here. So after we count the length, of course, we can apply the length to the width. 0.2 times 12.07, and we get 2.414 mm for the width. So you can see here, for the length, negative 12.07, why I divide by 2? Because I need to make sure that the slot is in the middle of the ground plane. And 2.414 also divided by 2 is also the same concept that I want to make sure that it is in the middle of the ground plane. And the material, I'm using vacuum here because we need to cut away the size that we had highlighted. So this is the slot that I have cut away. So after that, after we done for our slot, we now come to our substrate. The substrate also the same concept like ground plane. First create a brick with 30 times 30, but a little bit here is because I need to make sure that the substrate is down below the ground plane. So negative 3T, negative H. The H is represent the thickness of the substrate, that is 1.5 mm, and it will exactly down below the ground plane. And the material using here is Roger RT5870 that have represent 2.33 here. So we can see that the substrate is below of the ground plane. So after we had done for our substrate, now we come to our DRA. For our DRA, I decided to build a rectangular DRA that is more easy and more efficiency. So I decided to use 15 times 12 for my for the size of DRA, and 25 for the height, and the materials, and I'm using material 1 that is at epicenter 10 here. So this is easy for create the DRA, and the size you just need to make sure that it is fully covered and bigger than the slot. So after we doing the DRA, we need to calculate the line impedance to get the width of the patch. So we came to microns, calculate the line impedance. So through the figure, the W is the width of the page we need. So first, of course, we need to apply the value that we had. Number 4 for frequency, height for 1.5, W we don't know, and the epsilon 2.33, and calculate. Of course, we need to confirm that impedance is always be 50, so we can adjust the W here 4.49. So get the W 4.49 here to make sure the impedance is 50. So after we had get 4.49 for the width of the patch, we can build a patch that is 4.49 and make sure that your patch is longer and over the slot, then it is no problem for your patch. So after we had created the patch, of course, now we need to calculate for the port. Calculate for the port extension and build a port here. So first we need to select the face and then macros, solver, ports, calculate ports extension coefficient. So this is the W 4.49 we get, and the height 1.5, and the anterior properties 2.33, and we can get K for 7.6. So now we look after the waveguide ports. The K time H that red in color, that means we need to extend both sides, and then down below the and then also extend down from the substrate. And the H is need to make sure that it's fully covered from the substrate, start of the substrate, and at the end of the K times H. So we look to our left hand side, the port. So after that, we can build a port here. So after doing all of this, the rectangular DRA is completed, and we can start to simulate it. Because the simulate need take some time, so after we simulate, we will get an X parameter graph like this. It can show us it's your antenna work functionally and efficiency. So through this S parameter, we can also analyze the bandwidth and the gain of the antenna. So after we have calculated both of it, we also will get a table max gain over frequency, and also the far field. We can fill in and get a radiation pattern here. The radiation shows us the direction of the antenna radiated, and this is the example for frequency 5.5 radiation pattern. So this is all from me to present about my rectangular DRA. Thank you.